In the last two lectures, we have obtained the expressions of current gain, voltage gain, power gain, input impedance, and the output impedance. In this lecture, we will find out the overall voltage gain, and overall current gain. We will start with overall voltage gain. Overall voltage gain is represented by A subscript Vs, and overall voltage gain is defined as the ratio of output voltage to the source voltage. Output voltage is equal to V2 and the source voltage is equal to Vs. So AVS is equal to V2 divided by Vs. I will multiply the numerator and the denominator by input voltage V1. So we have V1 divided by V1, or we can write voltage V2 divided by V1 multiplied with V1 divided by Vs. V2 by V1 is equal to the voltage gain. The voltage gain is equal to V2 by V1. So the overall voltage gain is equal to voltage gain multiplied with V1 divided by Vs. You can definitely remember this form of the overall voltage gain. In the next step, we will find out V1 by Vs, and for this we need to refer this circuit. The input impedance is equal to Zi, and the input impedance means we have impedance equal to Zi. Here we can redraw this circuit. In which the source voltage is equal to Vs, then we have resistance equal to Rs, then we have the input impedance Zi, and using this circuit we will find out V1 by Vs, and you can clearly see V1 is the input voltage and it is the voltage across the impedance Zi. So we have voltage V1 across the impedance Zi, and let's say current flowing in this circuit is equal to I. So by using Kirchhoff's voltage law, we have Vs, polarity of Vs is like this. So we have Vs minus IRs minus IZI equal to 0. So the current I is equal to Vs divided by resistance Rs plus impedance Zi. The input voltage V1 is equal to IZI drop across the impedance Zi, and we have already calculated the expression of I, which is equal to Vs divided by Rs plus Zi. So V1 is equal to Zi Vs divided by Rs plus Zi, and from here we can find out V1 by Vs. So V1 by Vs is equal to Zi divided by resistance Rs plus Zi. Now we will put this value here. So the overall voltage gain AVS is equal to voltage gain inside the bracket impedance Zi divided by resistance Rs plus impedance Zi. So this is the final expression of the overall voltage gain. And if we consider the case of ideal voltage source, this means Vs is ideal, then resistance Rs is equal to 0, and when this happens, the overall voltage gain is equal to the voltage gain. So this is very important point to note down. The overall voltage gain is equal to the voltage gain when we have ideal voltage source, because resistance Rs is equal to 0 in this case. Now we will move to the next part of this lecture, in which we will calculate the overall current gain. The overall current gain. The overall current gain is represented by AIS, and to find overall current gain, first we need to define it. The overall current gain is equal to the ratio of output current to the current delivered by the source. The output current is equal to IL, and let's say the source is delivering the current IS. So we have overall current gain AIS equal to the load current divided by the source current. I will multiply the numerator by the input current I1, and I will also multiply the denominator by the input current I1. So we have I1 by I1. We can also write it as the load current IL, the load current IL divided by the input current I1 multiplied with the input current I1 divided by the source current IS. The load current IL is equal to minus I2. The load current IL is equal to minus I2. So we have minus I2 divided by I1 multiplied with I1 divided by IS. Minus I2 by I1 is equal to the current gain. So we have AI multiplied with I1 divided by IS, which is equal to overall current gain. You can remember this form of the overall current gain. In the next step, we will find out I1 by IS, and for this I will draw this circuit in which we will consider the source current IS. We have the source current IS, the resistance RS is connected in parallel with the source current. This is how we convert voltage source to the current source. The resistance RS is connected in series with the voltage source, and you want to convert it to the current source. Then you have the current source and the resistance. The resistance is now connected in parallel with the current source. This is basic thing to do. You can also convert the current source back to the voltage source. The resistance is RS, and we have the input impedance equal to ZI. This is ZI. Current through the input impedance is I1, the input current. I will use current divider rule, and by using this I will find the current I1. Current I1 is equal to IS multiplied with resistance RS divided by RS plus ZI. This is using current divider rule, very simple rule which you can follow, and from this we can find out I1 by IS. I1 by IS is equal to resistance RS divided by RS plus ZI. We will put this in this equation, and we have overall current gain equal to current gain inside the bracket resistance RS divided by RS plus ZI. So this is the final expression of the overall current gain. I hope you now understand how to obtain the expressions for overall current gain and overall voltage gain. In case of ideal current source, resistance RS is equal to infinity, and when resistance RS is equal to infinity, the overall current gain is equal to the current gain. There is one more thing I want to explain in this lecture. If you remember the last two lectures, we encountered with delta H. Delta H is equal to HI HO minus HF HR. We will try to prove this. The first H parameter equation is V1 equal to HI I1 plus HR V2. The second H parameter equation is I2 equal to HF I1 plus HO V2. We can also express the two equations in the matrix form, and we have 2 by 1 matrix having the elements V1 I2 equal to 2 by 2 matrix having the elements HI, HR, HF, HO multiplied with another 2 by 1 matrix having the elements V2 I1. Let's say this matrix is matrix D, this matrix is matrix I, the D is bold capital D, this I is bold capital I. We generally represent the matrices by bold capital letters like capital A, capital B, etc. Here we are representing this matrix by capital D because these two variables are dependent variables, and here we are representing this matrix by capital I because the two variables are independent variables. I will represent this 2 by 2 matrix by small h. I am just representing it by small h because we have to prove delta H equal to HI HO minus HF HR. I will only consider this 2 by 2 matrix, and we already know we can find out determinants of a square matrix only. 2 by 2 is a square matrix, so we can find out determinant of H, which is equal to HI multiplied with HO, HI multiplied with HO minus HF multiplied with HR minus HF multiplied with HR, and the another representation of determinant is delta H. So delta H is equal to HI HO minus HF HR. So we have proved this, and this is all for this lecture. If you have any doubt, you may ask in the comment section. I will end this lecture here. See you in the next one.